All right, so welcome everyone. Brains full yet? I know I asked that in my last talk, if you're in my last talk, but if your brains aren't full yet, well, hold on to your butt. This is Understanding Probabilistic Data Structures with 112,092 UFO sightings. If you're not impressed with the probabilistic data structures, hopefully the UFO sightings will be entertaining. My name is Royse. I'm a developer advocate at Redis. I like to joke that there are three things on this slide that matter. One of them matters to you, the audience. One of them matters to me, the presenter, and one of them matters to my boss. So who here uses Redis or has used Redis? A good percentage of you. My boss would like you to know that Redis is more than a cache. It has lots of other interesting data structures. Most people are using Redis just like to cache APIs and session data and that kind of stuff, but there's other things in Redis like probabilistic data structures, which we're going to explore today, and my boss would like you to know that. I only really care about how many people follow me on social media, so if you see that on Twitter there, give me a follow, if you still use Twitter. And I realize it's Twitter, X, formerly known as Twitter. I need to update my slides. That's the thing that matters to me. The thing that matters to you, and this is the most important thing on the slide, is that GitHub URL. So all of my code for all of my talks, the slides, the codes, the demos, are all out in a GitHub repo. And so if you want to go check out some of this code later and try this out for yourself, you can go to github.com/GuyRoyce. There'll be a QR code at the end. It will take you directly to the correct repo. But that's the part that matters to you all. And just a quick humble brag, yes, I do have guy.dev as a domain name. So 112,092. That's an oddly specific number, isn't it? It's precise, it's accurate. It is the number of UFO sightings that I have in a data set. It's a giant CSV file. There's 112,092 of them in that CSV file. This is the number of UFO sightings in the United States from about 1950 to probably about 5 years ago when I first downloaded this data. So it's probably a bigger number now. It's a lot of UFO sightings. It's a surprisingly large number of UFO sightings. And this data is made possible by two organizations. One is the National UFO Research Center, or Reporting Center in North America, in the United States, which is an independent organization of, we'll call them fans of UFOs, and they record all these sightings. And it's the result of this wonderful man right here. This is Tim Renner. Tim likes weird data. And so he goes out and screen scrapes the data from places like the National UFO Research Center and the Bigfoot Field Researchers Organization. He's got a big data set, turns them to CSV files, puts them on data.world, and then does fun data science stuff with them. The Bigfoot stuff is great. You use clustering algorithms to determine that you can find Bigfoot in the woods. Who'd have thought, right? He looked at I don't know that he really did any machine learning against the UFO sightings. He just did some basic analysis. He did a histogram of the day of the year that is the most common day for a UFO sighting. Any guess what common day in the United States everyone would be looking up at the sky? 4th of July, American Independence Day. And so that is, by like an order of magnitude, the most common day of the year for UFO sightings. Second most common day, New Year's. I always imagine like a father and son, they're out watching fireworks, and the son's like, "Dad, is that a firework?" "No, son, that's a UFO." He also discovered that the majority of these UFO sightings are within 60 kilometers of US air bases. Shocking. But these UFO sightings are delightful. I'll go through and read them occasionally if I'm bored and I want something funny to read. And the data is, that's pretty much what you'd expect. Every UFO sighting has a summary, which is sort of, not exactly a title, it's a summary of the sighting. So here we have 3 saucer-shaped ships, say that 3 times fast, high in the sky, metallic but no shine, rather dull gray. They hovered overhead in a V formation. That sounds like a UFO to me. This particular sighting was in Salem, Oregon, and it occurred on September the 15th of 1950 at 2 o'clock in the afternoon. So we've got a summary, city, states, a date, time when it happened in convenient ISO 8601 format. Every UFO sighting has a shape associated with it. This one was a disk. Sometimes the word shape is taken kind of liberally of what a shape could be. So later on, we'll see that shapes include things like object and light. I guess these are shapes. Every sighting has a duration. This is not like a fixed time. This is a string. So 15 minutes, a couple of hours, a few minutes, that sort of thing. There's a link to the New Fork website where you can go and look at the original reports, the full text of the UFO sighting. This is where the true joy is. And then a latitude and longitude of the city where they occurred at. So this is fun data. We're going to play with this to explore the most important question of all: what's a probabilistic data structure? So, what is a probabilistic data structure? Well, if you don't know the answer to that question, don't worry. You are in good company. When I first put this talk together a few years ago, I did a quick Twitter survey, and 119 people responded. And 58% said they had never heard of them. So that's 3 out of 5. So you probably haven't heard of probabilistic data structures. Another fifth of them had heard the term, but they probably heard the term in the question. Because we tend to be kind of literal-minded sometimes, don't we? So we're talking 4 out of 5 people have no idea what these things are. If you don't, that's great. That's why we're here. The other 20% were split more or less evenly between knowing what they were and having actually used them. And so when I put this talk together initially, when I first joined Redis, I had to put together a small talk on probabilistic data structures, which is what this grew out of. And I didn't know what they were either, and I had to learn. And so, like a lot of things that I do in my life, I learn about something, I get excited, and then I share it, even though I'm not an expert. So I'm not an expert, I'm a fan. But before we talk about what probabilistic data structures are, we need to talk about their evil opposite, the deterministic data structure. This is sort of their reptilian to the probabilistic data structure's gray. These are the data structures that we know and love and use every day in our code. Our languages have them built in. Things like lists or collections, dictionaries and hash tables, arrays and graphs and trees and stacks and queues and all those sorts of things. And they're called deterministic because they do what you tell them to. Like if I put something in a linked list and then I walk that linked list to find it, I'm going to find it. It's determined. And adding another thing to that linked list doesn't make it so that I won't find it. It's always there. Always does what I expect. I put something in there, it stays there, I can retrieve it. That's what makes it deterministic. And I'm going to look at one deterministic data structure in a little bit of detail, and we're going to sort of have a little bit of computer science data structures course flashback, because we're going to go through how hash tables work. Very briefly, maybe in just a couple minutes. And I do this partly because most of us haven't thought about how hash tables work since we had to pass our data structures class in computer science at university. And not all of you necessarily went to university to study computer science. Many of you have other degrees. Many of you probably have learned these things other ways. And so I think a quick refresher is in order. And the principles that are in hash tables, particularly the hashing of the keys, is something that shows up recurringly in probabilistic data structures. So understanding this and being refreshed on how this works is useful when it comes time to think about probabilistic data structures. And so a hash table, of course, is that classic key value store that we've all used. If you're a Python or a .NET developer, you would call this a dictionary. If you're a Java developer, you would call it a map or a hash map. If you're a Ruby developer, they actually call them hashes. And if you're a JavaScript developer, well, then you have my sympathies. And also, it's everything in JavaScript. Everything's an object. Except, as Dylan pointed out the other day, it's actually just a function. So we know what a hash table is. We've used these all the time. It's the key value stores that we use for all sorts of things. But why are they called hash tables? Well, it's because they make use of hashing functions. And we've probably all ran into hashing functions as well. What a hashing function does is it takes arbitrary data, sometimes a seed, depending on the particular hashing function, and then deterministically, for that particular data and that particular seed, spits out a signature or a number, like a 32-bit integer or a 128-bit integer, that is what you will always get when you run those function values through it. And so we sometimes use these cryptographically, so like there's the SHA-256. It distributes your data in, gets turned into values that are randomly related to each other. So like if you change one letter, it's not right next to it. It's just spread out randomly. We don't care about that for a hash table because cryptographic hashes are slow. But for hash tables, you want a non-cryptographic hash, something that's fast, like a murmur hash or maybe even a CRC16, where you can put the value in there and it'll calculate it very quickly. It needs to be evenly distributed, but it's okay if someone could guess what the value was. You're not trying to hide the values in your hash table. And so hashing function takes here, up here, we have the, like here's 6 bytes, goes to the hashing function, we can number out. Those 6 bytes are the ASCII/UTF-8 values for the name Scully. So if you're a fan of the X-Files. And it doesn't matter whether you're putting in 6 bytes or 6 gigabytes, you're always gonna get that same sized number out. Hash functions are used by hash tables to take the keys that we're using to look up our values and turning them into hashes and turning them into indices. So here we have the value of city. We're gonna put the city of Salem into our hash table. We run it through our hashing function, and we get this, say 32-bit integer. Our hash table here is an array right now of 10 linked lists. There are other implementations for hash tables. This is just the simple one I'm gonna use for this talk. And so since we have an array of 10 items, we modulus that number by 10, and that gives us an index into that array, a number from 0 to 9. And then we go to that, in this case, position 1, and we look at the linked list and say the linked list is empty, and so we add the city to it. We add the key and the value. And we add something else, we get another number, we add to that linked list. If we get to a linked list and we've got an index we've used already, we just tack it to the end of the linked list, assuming it's not in there already. And then when it's time to read something from our hash table, we go through this same process again, and we take the keyword city, we calculate the hash and the index, and then we walk that linked list until we find our keyword. And then we return our value. So this is how a hash table works. So I probably review for most of you. Hopefully review for most of you because I did cover it kind of fast. That's a computer data structures class in 5 minutes. So when we pick our data structures, we are often looking at their time complexity and their space complexity. I like to use the example of an array versus a linked list. So an array has a fixed size, and so its space complexity is O of n, where n is the number of items that we could maximally put in here, the biggest size. And so they tend to waste space. But operations against an array are O of 1 because you can go straight to the index you care about. So they're fast. Whereas a linked list is sort of the opposite of that. You have to walk that linked list to find the thing you're looking for, but the space complexity is nice and tight and compact. It takes up exactly as much space as it should. It's O of n, where n is the number of items in the list as opposed to the maximum size of the list. And so when we pick our deterministic data structures, we're often making this kind of trade-off. Do I want to use an array because I need speed, or do I want to use a linked list because I want to save memory? And so this is part of the decision in our deterministic data structures, but it's also not the only factor. Because lots of times, you don't pick a hash table, you don't pick a dictionary because of its performance characteristics, its complexities. You pick it because you're storing key value pairs. And so that is sometimes that capability is part of your decision as well. And there's another thing that you can choose as a trade-off versus time and space complexity and the capabilities, and that is accuracy. So you can select data structures that will lie to you. And I know we're all kind of twitching on the inside. Like, no, my data structure must always give me the perfectly correct answer all the time. Computers are precise, that's what they're for. It must be always correct. I do not want my data structure to tell me something is in my set when it's not, or to say something isn't there when it is. I want 100% accuracy. Well, that's true until you got to scale to 1 billion items. Let's say you're a large online company, a service provider like let's pick on Facebook in a good way. And how many users does Facebook have? 1 billion, 2 billion? What if I want to sign up for Facebook and I need to pick a username? How am I going to determine if that username is taken? Can I do select star from users at Facebook where username equals the thing I want to use, and then do just to go through the entire thing and find every user until I match it? That is not going to work. And so if you had something that could lie to you and say, it's probably not taken, that might be worth it. Because you can get orders of magnitude of time improvement and orders of magnitude of space improvement by sacrificing accuracy. This is the essence of what a probabilistic data structure is. And if you've actually been using these your entire career and you don't even know it. Because this image here of the Devil's Tower in Badlands in Wyoming in the US, made famous by Close Encounters of the Third Kind, Richard Dreyfuss, and a pile of mashed potatoes. If you get that joke, you're over 50. Yeah. This picture right here, it's a JPEG. You see that pixel right there? That one right there, the blue one? It's the wrong color of blue. Do you care? You do not, because you see a beautiful picture of the Devil's Tower. And that little bit of lossiness makes the JPEG smaller than it should be. And you lose some of that data, but you still have the image. This is kind of how probabilistic data structures work. Making sense? Cool. Let's get into the details. Let's talk about some of the types of probabilistic data structures and the patterns they have here. So a lot of probabilistic data structures, you can think of them as sets that are weird. So, you get a set, you can add things to the set, you can test that set for membership, get the cardinality of it, how many things are in it. You can do unions and intersections and differences on the sets. Probabilistic data structures are sets that can't do all of these things and might not do them with 100% accuracy. Some probabilistic data structures are focused on membership, where you add things to the set, and then you can say, hey, data structure, is this thing in the set? Yes or no? And it'll say no, or probably. You can get the cardinality, so you can add things to a set, and then say, how many things have you added? And you can get a number that's accurate enough. So like in the case of testing for membership, that might be a good way to solve the username problem. If I add all my usernames to this one here, and then I say, is this username taken? If it says no, then I know it's safe to use. And if it says probably, then I know that I won't hand it out. And if it's wrong, then it just means that username's never used. But it scales. In case of cardinality, this might be used to determine the number of unique viewers on a video. Add all the usernames to the set. And then you say, how many usernames are in here? If there's only 20, it's going to be pretty accurate. But if there's 300 million, and that 300 million is off by 2%, do you care that it's actually 29,999,920 as opposed to 300 million? No, it's a perfectly reasonable trade-off. So cardinality can solve those sorts of problems. You've got frequency, where you want to get counts of things. This is a similar sort of problem. This sort of stretches the definition of a set a little bit, because now I'm adding the set items to the set multiple times. I'm getting a little score associated with them. But frequency will let you store the frequency of different things. I don't have off the cuff a good example of this. I know there's a good example, I just can't think of it right now. But this is another probabilistic data structure where the counts are a little bit off, but they're close enough. And so as you add things to it, it'll say, well, the star was added 5 times, the square was added 4, that sort of stuff. You've got ranking, where the counts aren't stored, but the order is. So the counts behind the scenes are very, very inaccurate, but they're all proportionally inaccurate. And so I have an ordered set where I don't know the count very accurately, but I do know which one's number 1, which one's number 2, which one's number 3. This can be used for any kind of like trending topics, or you could look at IP network traffic against your servers and say, which IP addresses what are the top 5 IP addresses hitting me? Okay, that's probably where the DDoS is coming from. And of course, you can also take these sets and do similarity comparisons, where you can see how similar is one set to another. You can do this with regular sets, of course, but you can also do it with probabilistic data structures. When it comes to probabilistic data structures, we've got a lot of choices here. I'm not going to go through all of these. I am going to mention that the ones that have the little red daggers next to them are part of Redis stack. And then hyperlog log itself is just part of vanilla Redis, core Redis. The ones in blue that are highlighted are ones we're going to talk about today, assuming I don't go too long, which I'm going to try really hard not to do. So we're going to talk about Bloom filters, heavy keepers, and MinHash. Bloom filter is part of Redis stack. Heavy keeper is part of Redis stack. MinHash is its own thing. It's not part of Redis. I mentioned Redis stack really brief, so here is our advertisement. So Redis stack is just open source Redis that you've probably used or used through a vendor with extra modules added onto them to add new commands and data structures, including JSON documents, search capabilities, time series, and relevant to this talk, Bloom filters, which is one of the data structures. Bloom contains all the probabilistic data structures that were marked in that previous page. You can just Google Redis stack, or you can sign up for Redis stack in the cloud at redis.com/try-free. So, add over. Let's look at Bloom filters first. So a Bloom filter is probably the easiest one of these to get your head around of how it works. Bloom filters, of course, are sets, and you can add things to the set of a Bloom filter, and you can ask it for membership information. Is this thing in the Bloom filter, yes or no? And it will respond with no, definitively no, I know it's not in here. There are no false negatives, it's only true negatives. Or it will answer with probably, which means you can get both true and false positives. So no or probably. Bloom filters are cool because they are a fixed size. They never grow. So when you create them at a particular size, and they will never get any bigger. Fixed amount of memory. And every single operation on a Bloom filter is O of 1. So everything is constant time. Sounds impossibly good, doesn't it? Well, here's how they work. And for use case, of course, this is the username use case that I gave example. That's a great use for a Bloom filter. It's also good for deduplicating data. But here's how they work. So you've got, in a Bloom filter, you have some hash functions. Remember hash functions? With their associated seeds. And you've got an array of bits that's of a fixed width. So when you create your Bloom filter, you say, I'm going to use, in this case, we're using 3 hashing functions, and we're going to use 10 bits. This is obviously a tiny, useless toy version. You would use more functions. You would use a lot more bits. And probably have a multiple of 8. So what you can do with the Bloom filter is when you go to add something to it, it'll run through these hash functions. We're going to go through how it works. We're going to put in UFO sightings to see whether we've seen them before or not. So we're going to add it, and then we can say, have I seen this UFO sighting before or not? And if I have, then I'll double check. If I haven't, I'll go ahead and add it to my UFO sightings. And so the first UFO sighting we're going to look at is probably my favorite in the set. It's Megatron in the bushes. This is one of those things when you're scrolling the file, you just can't not look at it. This is the story of a couple of gentlemen, I use that term loosely, who were driving down, I believe, a New Mexico highway late at night, and they pull off to the side of the road because they have to take care of a important and necessary bodily function. Alcohol was probably involved. And so they pull over, and they go find a bush to take care of this necessary bodily function behind. And as they approach the bush, they hear that sound that Megatron makes when he transforms. And not the one from the movies, but the one from like the 80s cartoon. You know that sound. That's my impersonation of Megatron, by the way. And so they hear the sound, and they understandably freak out. And so they hop back in their car, and they go tearing down the highway, and these lights come up from behind the mountain and chase them down the highway like 60 miles. And I'm sure they were totally not high. It's a great story. This is why I enjoy reading these. Megatron in the bushes. So we want to know if we've seen Megatron in the bushes before or not. And so we want to add it to our Bloom filter. So what happens is we take the data in Megatron in the bushes, we run it through our hashing functions, and get our hash values. And then we modulus it, just like we did with the hash table, with the width of our bit array. So in our case, that's 10, giving us indices into that bit array. And then we set them to 1. And that's it. Now the Megatron in the bushes is in the Bloom filter. Now we can't get that back out of the Bloom filter. It's gone. The data is hashed away. But if we want to read it, we can run Megatron through the bushes through the same process, get the same indices, and look and say, are all the values 1 at these indices? If they are, then Megatron in the bushes is probably in the Bloom filter. If any of them are 0, it's not, because nothing flipped that bit from 0 to 1, therefore it must not have ever been added. So we can get a definitive no, but we can only get a probably when we check to see if something is there. And the reason is because, well, let's add something else and we'll see why really easily. And some of you may have figured this out already. So we're gonna do the next UFO sighting, the wonderful, grammatically correct and yelly case typed, I seen a UFO when I was about 13 years old. It's actually in all uppercase in the data set, and the grammar is wrong in the data set. I am proud to say that this is submitted by someone from my hometown of Columbus, Ohio. We're an educated lot. And so when we run this through the calculation here, we get different indices. But one of them overlaps right there, right? The circled one. That one overlaps. So before we got 0, 5, and 6, this time we got 2, 1, and 6. But that doesn't matter. This is why we have multiple hashing functions. The hashing functions, you'll get some collision, but if you don't have 100% collision, then you can still get a true or false response. You can get a no or a probably back. So it still works. And so we can go in and look up Megatron in the bushes and still get all 1s, and we can look up I seen a UFO and still get all 1s, and it works. Now, obviously, you can see that this is going towards being full really quickly. Right? We've already filled up half of our bits. And so normally you would have a lot more bits. You might have more hash functions. The hash functions mitigate the impact of the collision because you have to collide on all points for it to matter, but fills up the bit array faster. And so the more hash functions you have, the more bits you need to have. So it gets bigger, but it gets a little more reliable. So that's the trade-off. So let's add one more thing to our Bloom filter here, another UFO sighting. And here we have investigators from the Bigfoot Field Researchers Organization observing a glowing green-blue sphere. And in this case, the indices that are generated by going through the hashing functions are all things that are in there already. And so if we add this to the Bloom filter, it doesn't change the state of the Bloom filter. If we then ask it, is this in the Bloom filter, it will come back as a positive. Now, if I hadn't added it, that would be a false positive, but if I did add it, it would be a true positive. Right? That's the probabilistic part here. If I had added things in different orders, then different things would come up as probably depending on the order I added them in. So this is where it gets kind of weird. This is what makes it probabilistic. There's some math on determining how big your probabilistic data structures are. I'm not going to go into the details of it, so you can look at this math if you want. It's not as hard as it looks, but there's an online calculator that does this for you. So you really don't need to do the math. Generally what you do is you just try and guess, like I know how many items I want to put in it. And I know I can make a guess at the number of bits. And I can calculate the number of hashes, and then I can calculate the probability of a false positive rate, and then I can zoom in on it. But it's just easier to use the online tool. This is more here for reference. So Redis has Bloom filters in it. They're very easy to use. There's a command called bf.reserve, which will set aside a Bloom filter for you. You can give it the error rate that you want, which is used to calculate how many bits and how many hashes it's going to use. You can give the capacity, which is also used to calculate that, and then you can just use it. And using it is very easy. There's the bf add command, and you give it a key name and the thing you want to add. So here I've added disk and light. Or there's the BF mad command, which always makes me laugh a little bit because that's actually an organization in the US, the Mothers Against Drunk Driving, which I think totally relates to the Megatron and the Bushes story. But you can see what's interesting here is that I'm adding light a second time, right here, and I'm adding lighting teardrop, and it returns 0 or 1 to tell you whether you've modified the state of the bloom filter or not. So you can actually just add something and find out whether you've changed it or not. You'll know whether it's a duplicate or not. So light comes back as 0 because the bloom filter didn't change. Then you can use the BF exists command and just say, is this here or not? And there's an mexists as well that does that for multiple things, the variadic version. I always think mexists is kind of funny. It looks like mexists, which feels like some sort of, I don't know, it feels south of the border to me. So that's bloom filter. Lots of uses for them. You can dedupe data. You can do username lookups, all sorts of things. Let's look at the next one, MinHash. We've got 13 minutes and 59 seconds. I think we're going to get through this. So MinHash is used to determine the similarity between documents. So what MinHash really does is it takes a document like prose, like maybe we've all written term papers, and it boils it down to a set of numbers that we can compare to another set of numbers to see how similar they are. And so you could use this to determine, for example, I think it was Alta Vista. Folks at Alta Vista created this algorithm originally. And it was to determine whether the web page had changed enough to justify re-indexing it. But you could also use it to detect, plagiarism. How similar are these term papers that we all wrote here? Maybe we were all in a class, we all wrote term papers, and Professor Dillon wants to see if you all cheated from each other or not. He can compare the term papers using MinHash and set similarity. So in order to understand set similarity and MinHash, the first question is how the hell do we compare a couple of sets? Well, we can compare sets using a thing called Jacquard similarity. And it's fairly straightforward. Here we have Scalder and Molly, face swapped. I love this picture. They look like they're a synth pop band from the 80s. And Scalder has a set of UFOs, states in the United States in which he's seen UFOs. And so he's seen them in California, Nevada, Oregon, Wyoming, New Mexico, and Ohio, which is where I live, Ohio, not New Mexico. And then Molly on the right, she has seen UFOs in Florida, Kansas, South Carolina, West by God, Virginia, New Mexico, and Ohio. And so to calculate the Jacquard similarity of this set, we take the cardinality of the intersection. So that would be the number of items common between the two sets. So New Mexico and Ohio, so that's 2. New Mexico, by the way, is Area 51. Ohio is Hangar 18, where allegedly the bodies of aliens are stored in Dayton, Ohio at Wright-Patterson Air Force Base. And so this sounds legit to me. So we get 2. The total set, the union of them, has 10 items, and so 2 divided by 10 gives us 20% similarity. Pretty easy calculation. But how can we do this for a document? Can we just take all the words in one document, put them in a set, take all the words in another document, put them in the set, and then see how similar they are? Well, no, because that's just going to tell us that the documents were written in the same language. Right. So how can we turn documents into sets that we could actually do this calculation on? Well, you can use a process called shingling. Shingling turns documents into sets by breaking into trigrams that overlap. So we notice 2 is the first trigram. Notice to our and to our left. You see how they overlay like shingles on a roof, hence it's called shingling. And so this creates a series of trigrams that you can then do the similarity calculation against. So here we notice to our left, further off into the mountains, a bright glow. This is the Megatron in the Bushes story. So we've got this document now, it's sets. And so now we can do that calculation, that same Jacquard similarity calculation against these strings. Got a set of strings over here, a set of strings over here. We can get the intersection and the union, we can divide them, and we'll get a similarity and discover that, for example, Scalder's report and Molly's report are 63.6% similar. And so Skinner is happy. Now, there's a problem with this approach, which is that this is slow. Because A, we're comparing strings, but B, more importantly, we are we're comparing strings for multiple documents. So if we do the example where we've all written term papers, and Professor Dillon wants to compare them all, then this is gonna, there's a lot of, it's n times n minus 1 connections, right? It's a fully connected graph. That's a lot of processing. So how could we make this faster? How could we turn these into integers? That's what MinHash does. So here is how we calculate Scalder's MinHash. So what we do is we take every value in this set that we've generated, every trigram created by the shingling. We run it through a hashing function. We get a set of hash values, and we take the minimum and put it into a new set. That's why it's called the MinHash. And we do that for the number of hashing functions we have. I've only used 3 here because it fits on the screen. You'd probably want to use more in practice. We do the same thing for Molly's MinHash, and we get different values. And then, now that we have these values, we could do the Jacquard similarity calculation on these values instead of on the document or instead of on the words. Now, there's a mathematical reason this works that, frankly, I don't understand, and I don't want to go through a proof on stage anyhow, and you don't want me to do that either. But it does work, and so this is how you do it. Worth noting that the similarity was not as precise with my example. It's a 50% similarity as opposed to 63.6. That's because I chose 3 hashing functions, not necessarily because it's any more or less accurate. So that's MinHash. We got top K. We'll go through this one, and hopefully we'll have time for a demo. And then I think it's lunch after that, right? Or is it a break? It's a break. So top K, which is actually made up of 2 things. We're going to talk about heavy keeper as the main component of it, but there's also a min heap in there as well. So what top K does is it ranks items. It's made up of a heavy keeper and a min heap, like I said. And you would use top K perhaps for, I mentioned network flows, who's hitting my website the most. Or you could use it, it actually works really well for trending topics. And you'll see why here in just a moment. So a heavy keeper is a fairly involved probabilistic data structure, but it builds on all the things we've talked about. So it's got a series of hash functions and their corresponding seeds over here. And then each hash function has associated with it an array of a fixed width, and then this array of buckets. Those buckets have a place for a hash value and a place for a count. So it's 2 integers. A brand new heavy keeper has all zeros and nulls in it. It's empty. So what we're going to add to our heavy keeper are common UFO shapes. We want to count them and say, what's the top 3 most common shapes of UFOs based on our data set? So we'll tear through our data and start adding them to the top K structure. And so let's start with object, which is a shape. And so we put the object through the hash. We get a number, like we always do. We modulus that number with the width of our array to get an index, like we've done several times now, and we get an index. We do this for each row. And here we get 2, 1, and 2. And so what we do is we go to that location, we say, is this position taken? Is someone using it? Is the count 0? If it is, then we're like, well, that one's mine. We put our values in it, and we increment our count from 0 to 1. So in this case, we now have an object, and it's set the values to 1 in each row. If we add object a second time, it's going to go through that same process, and we're going to go into that array. We're going to find the location in the array. We're going to look at the hash number, and we're going to say, there's something there. Does it match mine? Yes, it does. Then increment the count. And so now object is in there twice. And if we want to query it, then we just reverse this process. We run the value that we want to query through the hash, get the index, find all the things that match our hash, go through that list and say, does this match mine? Yes, it does. Okay, what's the count? It's 2. What's the count in the second row? It's 2. What's the count in the third row? It's 2. What's the biggest number out of all those? Well, that'd be 2. So we return 2. The count is 2. Object has been added here twice. So far, so good. Let's add a different shape of a UFO. Let's add light. the other popular shape of UFO sightings. And this one's a little different because we'd go through this calculation and we get, on the first two rows, we get an index where the hash is null, where the count is 0, where no one has claimed this. And so we just claim it and put a 1 there. Easy peasy, just like before. But in the third row, we get an index of 2, and we see that the hash value doesn't match our hash value. So what do we do? And this is where the data structure actually gets interesting. Because there's a chance that the count will be decremented by 1. So in this case, light is not going to take over that position, but it could erode it. And so there's a formula that we use, and we generate a random number to determine whether we erode it or not. And this formula is P, probability of decay, equal to B to the power of negative count. This B is a magic number. It's greater than 1, but also very close to 1. And so we do the math. And so the bigger that the count is, the smaller our number is going to be because it's a negative exponent. And the smaller the number is, smaller count is, the bigger the probability is going to be. And so it's a heavy keeper. Things that are heavy are less likely to be eroded when there's a collision. They will erode eventually, but they're less likely to. So if you get something that's got like in there 10,000 times, and then nothing gets added for a long time, it is eventually going to be worn away until it's erased from the heavy keeper. Because the heavy keeper will keep the heavy things, but only as long as it's really about the flow rate more than the fact that it has a big count. Whereas small things pop in and out all the time. And so in our particular case, we do the math, we get a 90.7% chance that this is going to be eroded. So we're gonna go ahead and say that we roll the dice and it comes up, yes, decrement. And so now, this position is still claimed by the word object, but its count has dropped by 1. And so when it comes time to query, if we want to query how often light is in there, then we do all the calculations like we did before. We get 1, 1, and not found. So we take the smallest number, or the largest number out of the ones we have, we get a 1. So light has been added to the heavy keeper once. An object, we get 2, 2, and 1. 2 is the biggest, and so object has been added twice. Now, this example preserves perfect counts, but you can see how these counts would always be wrong. They're always going to be less than the actual value. If it equals to the actual value, that's unlikely. And that's part of why it's probabilistic. Alongside this is every single time we add something to the heavy keeper, we get that count, and we shove that value and the count into a min heap and resort the heap. And if it gets filtered out, it gets filtered out. And if it swaps out something that's there already, it swaps something out. And then if we just want to get the top K items, we can very quickly say, just give me all the things that are in the heap. And so this is how you can just get the list of things. But you can also go and interrogate the heavy keeper and get the count. Top K is pretty easy to use. I am a little bit over, ain't it? I got 1 minute, 48 seconds. So top K reserve sets up a top K structure. You give it the width and the height, and you give it a amount of decay, and you give it the number of items you want to keep track of. There's functions to add, functions to query, count, and list, and it's easy to use. So I've got a demo here. I don't think I have time for it, but I'm gonna power through it real quick. The last guy went 10 minutes over. I can go over 2. So let's go ahead and get the demo going. I've got it going here. Here's all my data, just proof that there are indeed a lot of them. So I'm gonna go ahead and run my Python app.py. What that does is it's going to hit Redis and query 2 top K structures with the most commonly used UFO sighting word in the description and title and summary, and the most commonly used shape. And then I'm gonna, over here, I'm gonna run the build.py, which is gonna populate that Redis data structure by using natural language toolkit in Python to do that. So it's looking through the JSON file, or the CSV file now. Now it's going in and adding things to the data structure. I go into Redis here. You can see we've got these 2 data structures, UFO shape and UFO words. I can do like an FT or top K dot list UFO shapes, UFO. Now, hang on. There we go. And you can see these are the top 10 that it's found so far. Now that's not fun to look at, so I built a website that goes and just polls this every second. And we can see these are the top 10 most commonly used words in UFO sightings and the top 10 most common UFO shapes. Light is number 1, circle's number 2 here. Light and lights are the most common words, sky, object. These are kind of the words you would expect in a way. So that's my silly, useless demo. Let's go ahead and get back to the slides here, and then we'll wrap this up. We'll just let that run in the background so my battery dies. So here's some resources you can go check out. This PDF is out in the GitHub repo, so if you want to check these out. It's got places to find the data, information about these data structures, all that kind of stuff. And it's got everything that I talked about. Here's some stuff. I work for Redis. We have a Discord server. We have free classes at Redis University, and you can get Redis Stack at redis.com/directory. Here is the QR code that takes you to the repo. It will never give you up nor let you down or run around and take you to some website that it's not supposed to. So if you want to check this stuff out. And that's what I've got. So thanks a lot.